Hello, welcome to another problem session. Today we are going to do a very standard problem. This is a variation on a problem where the blocks and the pulley just go vertically, blocks go vertically. That's the this standard iTunes machine. And this is also iTunes machine, but in one of the blocks is able to slide frictionlessly on a slope. Okay, so a whole bunch of things here to mention that this problem actually assumes, and if that was not true, the solution I'm about to give will not be correct. Okay, so one thing, let's go over one by one. So this is a string is massless, which means the string, since the string is also moving as the whole thing moves, it carries participates in the motion and carries inertia with it, and if it was not massless, we will have to take that into account. Okay, and there will be a problem in later. We'll do just some rope falling down and how it affects other objects around it. But right now, that's the assumption. It's very another assumption we're going to make is this is a frictionless surface. So I'm going to just say if this is not a frictional surface, then there are two cases. Block M is actually not moving because of static friction. In that case, you're dealing with static friction, right? But if the block is sliding on it, then in that case you're dealing with kinetic friction. So there are two cases. Are they going to deal with a static friction or kinetic friction? Okay. The third very critical assumption we are making here, and I will prove at the end of today, is that this is a common assumptions made in regard to pulley problems when we are not interested in the rotation of the pulley. Then we usually tend to, you might say, factor out the pulley problem and separate out the pulley problem from the rest of the problem. To separate out pulley problem or less problem, you have to have two conditions for the pulley. Pulley has to be massless. Of course, nothing is massless, but the mass of the pulley, just like a string, mass of the pulley is much less compared to pulley is much less than M or big M, whichever is smaller, okay, is much less than smaller of the two masses. Frictionless means if I blow up the pulley, so here's the pulley, and pulley has a axle about which it rotates. Frictionless means no friction here. When the string is going like that, the string is actually not sliding on it. Normally, if it rotates, so which means between a string and pulley, outside part of the pulley, the wheel of the pulley, there is friction. We are going to assume that, so the pulley kind of rotates smoothly rather than the string sliding off. Actually, our problem is same as even if there's no friction, pulley will not rotate, this just will slide off. Okay, but that's somewhat unrealistic. We want to have realistic situation and have pulley rotate. So that's the setup of the problem. This condition, we can prove that tension this side on the pulley. So let's call it T2, and tension this side. These tensions have to be equal to each other in magnitude. Prove that T1 equals to T2 magnitude. Because you can see they are different in direction, but they will be so we are going to use that means I'm going to use a single symbol T. So that's this thing goes with all of this. If you get time at the end, probably not going to get time today to actually show you why that is the case. Okay, all right. Maybe we'll talk about this later. Or maybe at the end of this video I will add some more. Okay, so let's get back to this. Couple of things to notice here. If this is covering a distance delta h in time delta t, then this will be moving the same amount of delta h. This distance and this distance will be same. Let's call it delta h prime. So its speed v will be same as this guy's speed v. Why? Because the string is not changing its length. Because this length of the string is fixed, that provides a constraint. Since length of connecting a string is not changing, distance moved by m in time delta t equals to distance moved by big M in the same amount of time. This would mean speed of M equals to speed of big M. This would mean, of course, this guy's velocity is this way, and this guy's velocity. So velocity is not equal. Velocity is not equal. This does not mean velocity equal. Okay, because velocity is a vector. Speed is equal, but the direction is not changing during that time. You can say the acceleration of m equals to acceleration of big M. That means just use a common symbol A as this magnitude of the acceleration. Okay, now I'm going to do a free body diagrams for each one of them. So for little block M, tension is pulling up, gravity pulling down, and its acceleration is A. We're going to use the same symbol. So here you can use your axis. There's only one axis, very easy to say. mg minus t will be ma. You don't even need an axis. So if you did a y-axis this way, your equation will be t minus mg equals to minus ma, like that, because this will be negative y component. So this is equation 1. A free body diagram for this guy block will be also very easy to obtain. Tension is up the incline, normal is that way, and gravity is that way. This is theta, so this is theta, and the acceleration is that way. So here it's easier because acceleration is this way, to point x-axis that way and the y-axis that way. So here are going to be two equations, one along the x-axis and one on the y-axis. Let's look at x-axis. So t, there's nothing for normal, and it's going to be sine. So t minus mg, big mg, sine theta, because this time it's big M times a. Third, we don't need this, but we just write this down. N this way and mg is this way, so it's going to be n minus mg cosine theta equals 0. So because there's no acceleration component along the y-axis, so this is not needed for solving the problem of acceleration, but it gets generated. So if I multiply by minus, and this becomes plus, and if I add to get rid of tension, you get mg minus capital Mg sine theta equals to m plus m a, and this will give acceleration equals to m minus capital M sine theta over m plus capital M, this whole thing times g. Of course, you can see that these acceleration units are okay, so you can suppose we had a theta was like vertically up, so that will be theta will be 90 degrees, and so it will be difference of the masses, and masses are equal, then it will not go anywhere. So that looks correct. When theta was 0, then the only weight that's providing acceleration is just little mg. So it looks like two cases work out. So this is the answer. Okay, so I'm going to pause here, and so this completes the problem, and I'm going to have a couple of more minutes later to address this question. Okay, so welcome to the answer part of why the tensions have to be equal when Pulley's mass 0. So to understand that, you have to write a rotational equation motion for the pulley. So we have tension force T1 here and tensor force T2 here, and then at the axle the force is all around the axle, and we want to write that as a torque. So frictional torque is this, and gravity is mpg, and of course the axle is going to be also pushing back up, so there is a normal from axle is like that. But regardless of which way the normal is pointed here, it may be pointed some other direction depending on where it's pushing on, depends on these tensile forces. So that it's pointed at the center. We can say the line passes through the center, and the center is where the axis is coming out. That's the axis about which it's rotating. Okay, so if you write the torque equation, you're going to get, say, counterclockwise is a positive torque. Then this, let's take this up, like this way, tendency to be positive in the direction it was going. So let's take that as positive direction. So T1 times R will be one torque, that's positive. T2 will be opposite direction, so minus T2 times R. And from this there will be no torque, from this there will be no torque, but this guy's friction is a little bit away from the center, so it's going to have a torque, and this is given as a total torque. So this is if it's rotating this way, it's going to be opposite. So this is minus tau F. This is already some force, friction force times this little distance R, and that's equal to pulley is say half m r squared. That's its moment of inertia times this is the angular acceleration. So this is not zero. This is this is not zero because it is accelerating. When this MP, when this is zero, then this is zero, so that this whole thing is zero. Then this is zero means this is zero. All this has to be zero to turn out to be T1R minus T2R equal to 0. This will means T1 equals to T2. That's why in a massless pulley and frictionless pulley, you can assume that the tensions on the two sides are equal. I hope it gives you confidence that you can use this equality of tension in the problems where they tell you the pulley is frictionless and massless. All right, see you in another video. Bye for now.